Lecture 9, set 5, handshaking. We just saw an example in the previous set when we had a result R, which was basically the sum of the square root of P and square root of Q. And the way we solved it was by designing one square root function, and then we had a simple control finite state machine, which in which one clock cycle called the square root and computed the square root of P. The next cycle it computed the square root of Q, and basically just stored these values and added them in the registers to get the final value. So basically the same. Oh, this is going off the board. Same function was used twice, but kind of time multiplexing, so there was not, we didn't have two instances of the same module. The same instance was used, and we just passed, the variables through the same hardware. Now, what if things get a little bit more complicated? What if, I have a design where each of these square roots take more than one clock cycle? What if I have a design where the module that I'm trying to use and pass variable on is being used by someone else, and then I have to wait till it finishes what it was operating on. To address this case, the protocol that we use to address these case, so for more complex designs where we are reusing the same module, what we do is we are using a protocol called handshaking protocol. And handshaking is pretty simple. Usually the top level or the master program that is calling the other one is called the master, and then the slave is the one that we call the variables to. In this particular case that we had, the master was trying to have the value R, and then it was calling the square root twice as the slave module to do these operations for it. Now, just what happens is that the slave is of course in some idle state, and then the master wants to start the operation. So what it's going to do is it's going to send a signal start to the slave. I mean, this is of course the most basic case I'm covering. I'm going to cover a little bit more complicated scenarios as we go on, but like in the most simplest case, let's assume that the master is going to tell slave, hey, start the operation, and what the slave and it's going to send also the inputs to the slave. And now if slave is taking multiple cycles, so basically here what happens is that it's going to have a start and send inputs, and then this is going to do some operations, and we don't know how many cycles maybe the slave is taking to do the operation. Maybe the number of cycles is dependent on the values or the parameters that I'm passing, and it may not be known in advance. So then what happens is that I'm going to have designed some handshaking protocol. In the simple protocol that I'm doing now, let's assume that the master has this probe which keeps probing the slave, asking, are you done? And then this could be taking some cycles. Again, are you done? No. And then at some point, I'm going to ask, are you done? And the slave is going to say, yes, I'm done. And once this happens, what the output is going to be red because this is a valid output. And then this is, again, going back to idle state. So if I want to show it on this diagram, after it's the slave is done, it's going to tell the master that the output is ready, and then that it will have the data out to the master. Let's see how handshaking works in practice when we do the code, and how this actually impacts how handshaking can be a little bit twisted to have more variables, like, for example, if multiple people are calling the same slave, so on and so forth. Let's go through an example of this and see how that actually works in practice for the code that we just saw. We showed this kind of more complex code in the previous set. And as I mentioned there, the details of this code are not important. What is important is that we are having this a little bit more complex code that we were calling the same module twice and passing parameters and saving parameters. Last time we just did it in using just a clock in 2 states, and now we want to design this system where we have added handshaking signals to the master and slave. In this particular case, the slave is the square root function. The master is kind of the top level design that calls the slave function. And now, as you see here, the slave function, which is the square root, has these interfaces. It has as input start and data in, and as output signal it has ready and data out. So when we declare the slave, we need to declare these signals and make sure that we have them on board. So this is basically the declaration of the slave. It's similar to the one we've seen earlier, and again, the inputs, the details are not important. But the handshaking signal, as you see here, it has the input has the clock and reset, which we always have, but it also has the start and ready as they which are added to the regular list of inputs and outputs for the module. And these are used explicitly for handshaking. And then because we had that, if you remember from the previous what I wrote on the board, we had the master slave, and then we had the ready and start, and then we had the ready, the start was going in, the ready was going out, and then the data was coming out, and then we had some data in as well. So now what happens here is, we need to design that finite state machine that says, are you ready, are you ready, are you ready? So there are these 3-4 different states that we had in the design that we had. Here, if you remember, we have the start state where we also send the input, then we have the wait state, and then we have this ready state where the output is ready. So in addition to the idle state that we originally had, we have these 3 states, and if we are designing a master slave, we need to define these 3 states in the code. So as we are doing the slave, we need to do sequential logic or a finite state machine that controls this. So what it says is that if you are in the idle state, if the ready signal comes, we are basically, it basically means that you reset the values to 0. But if the start comes, then we go to the begin. So we go to the state 1, and the state 1 is that state where you do the operation, but the wait state is just going to be saying that this output is not ready. So the master would know that this is a wait state. And once this is value is computed, then it's going to say that the ready is 1, and then it's going to go to the idle state again. Exactly like that chart that we were showing in the beginning of the road. So basically, if the start, this is going to go to the state 1, and other than that, it's going to get the things ready. And the handshaking is going to have the similar handshaking signals have to be, or corresponding handshaking signals have to be also implemented on the master side. So master, remember the master had this signal going out of it, saying, in addition to whatever other input or output it's sending, saying, start the operation, and once it's ready, it's going to read the operation. So it's going to have this start and ready handshake signals, and then these are when it's going to call the slave is going to pass the variable start and ready to that slave. And again, we have a finite state machine which says, once this you want to call this other entity the slave, the start will be 1, and now the slave knows that it has to start operation, and it's going to send data as well. And once it goes to the wait state, and the wait state is basically looking for the ready signal from the slave, which we defined here. So it's connecting the slave to that ready signal. And once this ready signal is asserted, we know that the value of the output is ready. And then at that point, we are going to read the output as it is shown here. And then we are going to repeat the same procedure, just going to that wait state. And once the module is done, we know that we've computed this task twice, and then we are going to do this. So basically, in the handshaking example, we have this few start handshaking which transfers the data. Then we go in the wait state. Whenever this is done, it's going to handshake again, says things are ready. Then this is going to go to wait state compute, so on and so forth. Now, there is more than one style for handshaking. There's the style we just saw where, we had this wait state, which you kind of keep probing in that, every clock saying, are you done? Are you done? The other one is, if we have a fixed count for how much the wait should be, or which could be sometimes an overkill because we may not know always what is how much time it takes, but sometimes we know, so it's an easier, cleaner write style to do that. And then we go to the output which was the idle state at this. Here are two examples of what we have just seen. Here, the wait state is, as we described earlier, it's waiting for the ready signal from the slave until it's ready. Then it's going to stay in the wait state. The other one is when you have a counter, which is going to count, and if that counter reaches a certain state, we know that this is ready, and it's going to get the results. So naturally, the style 1 is easier to write code, but if the completion time of the slave module is variable, this is what is recommended to use. But if we know that exactly this many cycles are going to take for the slave modules to finish, then it's better to have a predictable control flow, and may be able to write better controller, similar to the ALU controller that we've seen in the last lecture. And the thing is, we need to know exactly how many clock cycles each one of these tasks will take. And if the other drawback could be that in the style 2, sometimes if the completion time is variable, we have to do the maximum amount of possible computation before we finish and go back to the master. There are other kind of a little bit more complex scenarios for handshaking. For example, if you have a module slave that is being called or is by other masters, then it may be busy. We may not be able to use the hardware resources. And now if we assert the start, in the beginning, in the middle, even for the same master, if you assert a start in the middle of a computation, it may mess up the computing. So the slave may have an additional signal, which is a busy signal, which says I'm gonna ignore every start request coming to me if if I've already accepted another job. And then in addition to the ready signal, we are going to check the status of the busy signal because before we assert a start. And this is of course especially important if we have more than one master module. So here again the same handshaking scenario, but we have one busy signal added to the handshaking scenario. Okay. So far we've seen kind of an example where we called the same module, but we have only one instantiation of it, but we kind of time multiplexed. We had a controller which said, I'm going to use this module twice, but I'm going to use it in different points of time in different states. And we did it either by handshaking or just by designing a controller finite state machine. But there was the combinational case where we only had, there is, remember, the function we are doing is that r equals square root of p plus square root of q. And now we could just go and have this square root of p and square root of q in two different hardware instantiations, and then just do the design like that. Then it's a combinator. You could even do a combinational design for that. And a combinational design, in some senses, it's nice because you only take one clock cycle, so it's faster. But as you see here, in terms of the number of LUTs, this is substantially more output because we are not reusing the output. This is substantially more hardware because we're not reusing the same function. And but here we are storing the values for the first pass of the function before we go to the second pass. So we add to the number of memory elements or flip-flops here, and here in the combinational you could also use the DSP units on the module, which we didn't discuss. But here again you see an example where we have more resources used, but the number of cycles, as you see here, is shorter, so the time is less than the sequential, because in sequential we are adding some control, and we are basically having a longer bit width. So the combinational approach is faster but requires more area. The sequential approach is slower but requires less area. So this is basically a design trade-off. There are, of course, other possibilities how we could design this. We could have this sequential square root module, in other instantiation, and these design decisions are always happening in practical design, and the designer's intelligence is to basically try to choose the best option. The tools are helping us optimize things, but some of these decisions are basically designer decisions, and they cannot be always automated. So the tips for this is basically make sure that each of the submodules or the modules that you have in your design independently work. So design test benches and try to make sure that the input outputs are behaving correctly before incorporating them. And first design the standalone modules, then add handshaking, and try to write test benches that include all possible scenarios. EC 111, Lecture 9, Set 6. This is just a super short video, just discussing in a high level the project 2. The description is given in the post. That this byte rotation is important because we are basically learning how to access memory and how to do a little bit transform on the memory and then write back to the memory. That's the significance of this project. You're going to use this operation in the final project and in the projects that we have upcoming. So basically, the byte rotation is just like some simple transform about the content of the memory. The intention is for you to learn the memory model that we will be using for the rest of the projects. Good luck.